Following on from product rule, we now on to quotient rule. Product is where they're multiplying. Two functions are multiplying. Now we have quotient rule where two functions are dividing. Here's some examples. The first example, a binomial over a binomial. Very simple, but this cannot be differentiated by the basic principles which we've done so far. So we look at it as u over v, where u is equal to x minus 2, v equal to x plus 3. Or define it as a function, f of x equals the same thing, where f of x is g of x over h of x, and g of x is x minus 2, and h of x is x plus 3. A similar one, but where we have a second degree expression over a fifth degree expression, but it's exactly the same principles as before, where we look at it as a function over a function and we define the two functions. And we can add more complex functions as well. For example, this function below here, the square root of 1 minus x squared, is a candidate for chain rule, because there's an inside function, 1 minus x squared, and then an outside function, square root. So if we are using this in quotient rule or product rule, we have to use chain rule when we come to the derivative of this denominator. So let's have a look at what quotient rule is. But before we do that, let's just have a look at product rule. There's product rule. Derivative of uv by dx. So derivative of u times v with respect to x is du by dx times v plus u times dv by dx. So it's derivative of the first times the second plus the first times derivative of the second. Now have a look, there's not much difference in the numerator of product rule. Product rule has a numerator and a denominator, but I'm going to go to quotient rule now and have a look here. You'll see there's the product rule. Now if you look at quotient rule, it's precisely the same, except we have a negative instead of the plus from quotient rule, from product rule. So it's derivative of u with respect to x times v minus u times derivative of v with respect to x, all over v squared. In the simpler notation we've used, y prime equals u prime v minus uv prime over v squared. It comes off the tongue so much more glibly, so much simpler than all this derivative with respect to x and everything else. Y prime equals u prime v minus uv prime over v squared. And there we are. Derivative of the quotient u over v, so it's a denominator under a numerator. Derivative of u, the numerator, times v, the denominator, minus the numerator times derivative of the denominator v, all over the denominator squared, v squared. Here it is in functional notation. Same thing. We have g of x over h of x, so derivative of g of x over h of x with respect to x is g prime h minus g h prime over h squared. Loosely speaking, derivative of top times bottom minus top times derivative of the bottom over bottom squared. So there we are. We'll keep those reminders. 3 different ways we can use them. This can easily be illustrated using chain rule and product rule. So just let's show where this quotient rule comes from using product rule. So there we have, if we have y equals u over v, it's the same as u times v to the minus 1. Now we can use product rule. dy by dx equals du by dx times v to the minus 1. So it's the first derivative of the first times the second plus the first times derivative of the second. Now put that v in brackets because v is itself a function. So we have a function to the minus 1. So this is actually a chain rule. The outside function is something to the minus 1 and the inside function is v. So therefore, this stays the same. U times, now derivative of that, minus 1 multiplies down and subtract 1 off there. So minus v to the minus 2. But now we have to multiply by the derivative of the inside function v. And that gives us the slightly simpler form. All I've done is I've put the negative exponents, I've taken them to the bottom. And putting over a common denominator, we get the quotient rule. There it is there. Let's do an example. We cannot do this by basic differentiation. So we're going to have to use quotient rule. So we see u as being the numerator and v as being the denominator. There's our quotient rule. Notice I'm using the abbreviated form now, so much easier. So that's equal to derivative of u is 3x squared minus 2, and we multiply by v as it is, minus, not plus, minus, and then u as it is, times derivative of v, which is 5. And we have to put it all over v squared, the denominator squared. Simplifying a bit, and there we are. Let's do another one. This one where we have to use chain rule within it. Yeah, so we have u equals x, the numerator, and denominator square root of 1 minus x squared, 1 minus x, which I've written as 1 minus x all to the half. So there is quotient rule. So derivative of u prime is 1, and v is exactly as it is, minus u, which is x, times, and now we have to differentiate the outside function, which is half 1 minus x to the half minus 1, so it's half 1 minus x to the minus half, multiplied by the derivative of the inside function, which is minus 1. Now that's a bit difficult to deal with, but there's a very simple way around it with fractions over fractions or with negative exponents. What I'm going to do is I'm going to say, why don't we multiply top and bottom by 2, because that'll get rid of the half, and top and bottom also by 1 minus x to the half, because that'll cancel out that half on the top there. There we are. Notice that I'm really multiplying by 1. I'm not changing anything. This is the opposite of factorization. I mean cancelling. When we are cancelling, we're simply dividing top and bottom by the same thing. So now we're multiplying top and bottom by the same thing. So now 2 times 1 is 2. X, 1 minus x to the half times 1 minus x to the half is 1 minus x. Minus x, the 2 cancels with the half, the minus 1 changes that to a plus, and that becomes 1 minus x to the naught, so it's gone. And this below, we're multiplying by that, so we're going to add the exponents. We have the 2 and we have our 3 over 2. which we can simplify it to there.